Okay, so today, the last lecture of the semester, and I can see in your faces you're just as heartbroken as I am about it. It's been fun. Can't wait to see where you guys go as you continue your journey through Cincinnati State. So, the plan is here. I have the final exam ready. It is online. It will be live at 5 o'clock this afternoon. And you will have until Friday midnight to complete it. I hope that gives you enough time. I'm sure hopefully you got a couple hours in your window or window of a couple hours this week. Uh, let's see, what is it? 100 questions and you have 100 minutes to complete it? No, I'm just kidding. I'm just kidding. Uh, 25 questions, it's worth 50 points. I'm giving you 3 hours to actually complete it. So, with that, as soon as you open it, that's when the clock starts. You cannot save and pause and get out of it and come back into it. This is a one shot. As soon as you open it, see it all the way through to the end. I do believe that 3 hours should be more than enough. Um, a lot of the same formats from the quizzes. There's going to be some multiple choice, fill in the blanks, true, false, matching some definitions. I don't think it's anything too terribly crazy. And actually, you may recognize some of these questions because I'll tell you now, I did lift quite a few of these questions from quizzes throughout the whole entire semester. So, what I was hoping to do today was kind of run through some of the lectures quickly, just a kind of a brief overview, hopefully, maybe freshen up some things in your minds. But what I would like for you to do, obviously, is go through your class notes that you had taken, go through the book, and you look at prior lectures, go through the chapters, things like that, and study up a little bit. Um, if you do have this lab time kind of already blocked out, that might be a great time to go ahead and take this final. Um, Again, I'm not trying to throw any curveballs or do anything too terribly crazy or anything like that. Let's see what else. All the multiple choices, I said randomize the answers, so hopefully they're not all C or A or B or whatever. I do think that'd be kind of evil to do, but kind of funny at the same time. Overall, does anybody have any questions on the general format? So again, from 5 o'clock this afternoon till midnight Friday, that is May 1st. Another thing, I'm still trying to get caught up and finish all of the grades. So like I might have a couple quizzes or a couple labs kind of still hanging out there that I need to grade. Excuse me, I'm going to try to get that all done by this week, by Friday. Now, since the final exam is over at midnight on Friday, I'm probably not going to even start looking at that until like Monday morning. I have to have the final grades in by Wednesday. So somewhere between Monday and Wednesday, you will have your final grades. The content of the course, everything in Brightspace closes on the last day, May 2nd. I am not 100% sure how this works as far as if you log back into this class, you might not see any of the content, but will you still be able to access your grade? I don't know. If you cannot see your grade or wondering what is your final grade for this, shoot me an email. I'll send you that information just in case something weird with Brightspace. Like all technology, I know Brightspace is perfect, infallible, and never has any problems. And we all love it, right? We sure do. Okay. Anybody got any questions on tying up the end of the semester here as far as grades or format of the exam. Anything? Anybody? Anybody? I know I'm not the best instructor here, but I know I'm your favorite. I got a couple smiles. Okay, we'll run with that. Thank you. Take what I can get when I can. So this final will cover some things all the way from the beginning of the semester. Um, so yeah, again, look through prior labs, prior lectures, prior um, quizzes. Definition of surveying. What is surveying? It is the science, art, technology of determining relative positions of points above, on, or beneath the Earth's surface, or establishing such points. Cool. Geomatics, a term that can be interchanged with land surveying. This name is derived because of the manner and scope of practice in surveying have changed, part because of the recent technological developments and new tools for measuring and collecting data and establishing precise positions, computing, analyzing information. I don't know why I like that, precise positions. That kind of trips me up. I really got to think hard to get that out clearly. Geodetic surveying, plane surveying. So geodetic surveying is surveying that takes into account the curvature of the Earth. We use an ellipsoid, which is a mathematical model used to reference as a reference datum for establishing positions. ECEF coordinates, Earth-centered, Earth-fixed. That's what that stands for. Cartesian coordinate system, where calculations, equations are derived from solid geometry and calculus. Plane surveying. Plane surveying reference datum is a flat horizontal surface. Calculation equations are simplified using plane geometry and plane trigonometry. Any questions on any of that stuff right there? The next class you guys will probably be taking, if you take with me construction layout, I do kind of briefly touch on datums, but then further on you would take a geodetic control surveying class with me in the summers. That's where we really dig deeper into datums and stuff like that. But if anybody's got any questions, I'd be more than happy to try to answer anything. Geodetic surveying, taking into account the curvature of the Earth, and plane surveying is basically assuming that the reference datum is a flat horizontal plane. So some various types of surveys we do are control surveys, just establishing a network of horizontal and vertical monuments that serve as a reference framework for initiating other surveys. Topographic surveys, determining locations of natural and artificial features and elevations used in map making. Hopefully that one's a little fresher in our minds. We just talked about that recently. Boundary cadastral surveys deal with established property lines and property corner markers. Cadastral now generally applies to surveys of the public land systems. We have original surveys in that, which would establish new section corners in unsurveyed areas, retracement surveys to recover previously established boundary lines, and of course, hydrographic surveys to find shorelines, depths, bodies of water. Anybody got any questions on any of that? Construction surveying. So this is really what falls into the next class from here, the construction layout, where we are providing a horizontal and vertical position of proposed structures. Provide line, grade, control, elevations, horizontal and vertical positions for construction projects. So where's that road go? Where's that building go? Where's that manhole go? Things like that. As-built surveys, that's kind of like a topographic survey where you're just going out collecting data. This is documenting the precise final location and layouts and record any design changes of construction projects. So you construction folks may be out on job sites. You might see surveyors come out and as-built the storm sewer, sanitary sewer, the water line. Maybe you'd see as-builting foundations of houses and subdivisions, things like that. The surveying profession, so professional surveyors must have a thorough knowledge of mathematics, computers, surveying theory, instruments, geodesy, photogrammetry, remote sensing, economics, geography, geology, astronomy, dendrology, and very important boundary law. All U.S. states and territories have registration laws for professional surveyors. And just to add to that too, seems like every state has multiple pathways on how to become a professional surveyor. Any questions? Hey, keep moving. Slow down. Chapter 2 is all about the units, significant figures, and field notes. We kind of briefly touched on some of this, didn't get really too in depth on that. Therefore, the final exam will not get too terribly in depth on that, but there may or may not be something about units, measurements, things like that. I like to say that may or may not contain. We briefly talked about field notes, and I try to incorporate like kind of some of the field notes into some of the labs. I need to tweak some of that and make some of that a little bit better. Field notes in general, though, are the original permanent legal quality record of field work. These include measurements, sketches, and explanations sufficient for another surveyor to reproduce the work. For those of you that do get into surveying, particularly in, I'll say, sectionalized land, the public land system, where you're finding section corners and things, a lot of counties still have like a lot of the original notes from the original surveyors when they sectionalized this way back when, in the early 1800s. It's really cool, I don't know, just from a historical standpoint to look at things like that. Some general requirements of handwritten field notes: clarity, legibility, completeness, identification of the project, the crew, the date, use of ink. I think I've always used pencil in my life. And proper correction methods so the original record is preserved. There are types of field books, common formats and rulings, explains why bound pre-numbered books are used, and matches book types to typical surveying tasks. Different kinds of notes we have: tablature, numeric. Say, for example, like the level notes would be a tablature form. Sketches and descriptive text showing how they work together to convey both measurements and intent. The arrangement of notes explains the standard page organization, titles and identifiers, then data in consistent columns, and sketch placement. This is to support later checking and computations. Suggestions for recording notes. This introduces the data collectors and digital files as a modern form of field notes, stressing metadata backups and procedures so they match the reliability and legal standing of paper notes. You'll hear a a lot of surveyors say things like, you don't have to be right, you just can't be proven wrong. It's kind of a semi joke there. But in a way of not being proven wrong has to do a lot with the documentation and recording of data of the field work that was completed. All right. Anybody got any questions on that? Chapter 1's chapter 2. Quick stuff there. Horizontal angles are very important to surveyors. We measure two types of angles, horizontal and vertical. Talking about the horizontal, we have a couple different types. We have the exterior, deflection angles, interior angles, things to that nature. The majority of time, any angle that you come across will most likely be an interior angle and an interior angle measured to the right. Our total stations record all angles from their initial baseline, an angle to the right or an angle clockwise. Angles, bearings, azimuths. To determine locations of points and the orientation of lines, measurements of angles and directions are used. In surveying, these are called bearings and azimuths. The methods of direct angle measurements listed there, we did that horizontal angle lab earlier in the semester using a total station. That is where you would actually occupy a point, establish a baseline, and then turn and measure the angle quantity to another point. Methods of indirect angle measurements typically have to do with measuring distances and doing some computations, some basic triangle computations. So 3 basic requirements to determine an angle. One is a reference or starting line. 2 is a direction of turning. And 3, angular distance, value of the angle. That word distance, I remember seeing that in the book. That kind of threw me off. I don't like that, angular distance. But I'm not sure how. What would be a better way to say that? Angular value. Is this all kind of coming back? Everybody remember seeing this, reading about it, learning about it? Units of measurements, we use the sexagesimal system, if I pronounce that correctly, where we divide angles into degrees, minutes, and seconds. We can get into decimal seconds. We know there are 360 degrees in one full circle. There's 60 minutes in 1 degree, and there's 60 seconds in 1 minute. So kind of like a clock, if you think hours, minutes, seconds, where 60 seconds equals a minute, 60 minutes equals an hour or a degree. The types of angles, like we mentioned before, we have the interior angles, angles to the right, deflection angles, exterior angles, and angles to the left. Interior angles, we do this measuring on the inside of a closed polygon. Think of our horizontal angles lab. We had a 4-sided polygon. We measured all the interior angles of that. They are measured from the apex and have a mathematical check of the angles. So the theoretical sum of any polygon, regardless of the number of sides, That theoretical sum is equal to the equation n minus 2 times 180, where n is equal to the number of angles or sides. That's a pretty easy one to remember, right? We got that down, locked in our memories. We understand it backwards and forwards, sideways. Exterior angles to be measured on the outside of a polygon, also measured at the apex. They could be measured to use as a check, because we know the sum of the exterior and interior angles should equal 360 degrees. Hopefully a picture there kind of makes that look very self-explanatory. Angles to the right, measured clockwise from the rear to the forward stations. Angles to the left are measured counterclockwise, also from the rear to the forward stations. Pretty straightforward stuff there. Angles, angles, angles. We love our angles. Deflection angles, they are measured from an extension of the back line to the forward station. Allegedly, they're used in route surveys. I have very rarely in my life ever come across deflection angles used in seeing them in like any route plans. I do believe I've seen one once in a legal description. They are measured to the right or left depending on the direction. To the right, again, still would be clockwise, and this time we would say would be a positive angle. To the left would be counterclockwise, and that may be listed as a negative. The angular value of a deflection angle is always less than 180 degrees. Anybody any questions on deflection angles? I think this bottom really kind of helps drive home the point of that. Where you take your back sight line, you would project that forward, and then from that forward non-existing line, turn to your next station that you're going to travel in. Does that kind of make sense? Deflection angles, deflecting? I will take back what I said about the whole route surveying thing. What we do in construction layout, and we'll learn to calculate horizontal curves, we calculate what we call deflection angles to lay out horizontal curves. However, I never really have actually seen deflection angles listed in plans, personally. Meridians, real quick. Talking about the direction of a line. The direction of a line is the horizontal angle between that line and an arbitrarily chosen reference line called a meridian. That isn't necessarily always arbitrary because we have different reference meridians listed here as astronomic, magnetic, assumed, grid. Does anybody understand the difference between these meridians? Typically, meridians, we call these on a north-south line only. So your astronomic or geodetic or true meridian, at any point, the astronomic meridian is the north-south reference line that passes through the Earth's geographic poles. I am going to learn a little bit more about that. I've never actually taken any astronomic readings, but I think it's very fascinating to determine like north or determine where your latitude is on the Earth. I'm just going to go ahead and throw this out here now. When I was in Washington, D.C., I was talking with a retired NGS surveyor who has done lots of this type of work. They're going to actually be setting a reference, kind of a commemorative, what am I trying to say? Memorial type of a survey marker at the Cincinnati Observatory. Apparently at the time, like way back when, there were a lot of observatories built approximately on the same latitude across the United States. And all these observatories were taking astronomical reference readings to determine things like latitude and meridians. The one up here in Cincinnati, up in is that Mount Lookout? Mount Lookout, yeah. No, well, I think it originally started at Mount Adams, the Cincinnati Observatory over there on the east side. Um, what I think I'm going to do, I'm going to stay in the know when they're actually going to produce or place this marker, and maybe have that as a field trip for any of you surveyors next spring. Yeah. Yeah, I haven't seen a whole heck of a lot of it. I've never really been inside of it very much. That is cool. Pretty fun stuff. The magnetic meridian, which is kind of by your general compass, that is influenced by the Earth's magnetic field. Magnetic north by a compass, and that magnetic pole moves all the time. An assumed meridian would be established in any arbitrary direction to be held as true north and basing all other lines of the survey related to it. So just like it says, assumed. You're standing out there in the field and you go, yeah, that way's due north. We're just assuming. It's not based on anything. And grid meridian is used with state plane or other coordinate systems, other state plane coordinate systems, where I would say think of, well, let me kind of go back here. Your astronomic meridian or geodetic or true meridian is based on the Earth's geographic poles. So as you go from the equator to the North Pole or South Pole, those meridians converge and they meet at the geographic pole. Grid meridians do not converge. Think of a sheet of graph paper where any place you move east or west on that paper, those north-south lines are parallel and they do not converge. So that's kind of the difference between like a grid and an astronomic or geodetic meridian. Does that make sense? It just kind of makes me wonder what meridian did old Santa Claus use when he set up shop at the North Pole? I'm the only one on that one. Okay. Bearings are the acute horizontal angle between the reference meridian and the line. These are imperative to surveyors. They are on legal descriptions, as we saw in that survey plat lab. They are on survey plats as we put them on that plat lab. Bearings are everywhere. It is important to know and to remember bearing angles are always measured from the north or south, heading towards the east or west, and they are always less than 90 degrees. That is imperative to remember as a surveyor. An azimuth is a horizontal angle that is measured clockwise from the reference meridian. So we would pretty much always say that reference meridian is going to be due north. So it will be measured to the right or clockwise from that north and have values from 0 all the way around to 360 degrees. So if north is 0, due east would be 90 degrees, due south 180, due west 270, and then you're going to come back up around to hit 360 or 0 being due north. And the thing with that is you can also, bearings and azimuths are used to delineate angles. So you can take different angles and different bearings, different azimuths, and calculate the interior angle between those lines using those bearings and azimuths. Uh, Conversion between northeast, southeast, southwest, northwest bearings, how to convert those to azimuths, and likewise going from azimuths back to bearings in the various quadrants. This is all still on Brightspace, so please feel free. I'm just kind of running through it, just aloud, talking out loud about what's already there for you to study. But if anybody has any questions, please raise your hand, speak up. I'll be more than happy to try to answer anything if there's any little gray areas. Yeah, cool. I almost hate to list mistakes because I don't want to put mistakes in your head. So then all of a sudden you're kind of thinking about it and could possibly have a mistake. But some of these could be mixing clockwise and counterclockwise angles, confusing meridians, interchanging bearings for azimuths, failing to change bearings letters when using a back bearing, using the angle at the wrong end of a line, not completing traverse or including last angle to recompute the starting bearing or azimuth as a check. Yeah, all kinds of stuff. I would say probably one of the biggest ones to be careful of would be recording decimal degrees or degrees, minutes, seconds incorrectly, getting those switched. That would be the one I would be very cautious of and be very careful of. Adopting an assumed reference line is difficult to reproduce. Talking about traverses, there are a series of consecutive lines whose lengths and directions have been determined from field measurements. A closed traverse starts and ends at the same point. So, like the horizontal angles lab we did earlier in the semester. We started on one point, ran around, measured all our interior angles, and measured back to that same starting point. There are two types of traverse. There's a closed traverse and an open. The closed is what you should use 99% of the time when you're doing a traverse out in the field. That's going to be, like I said, starting and ending at the same point. If you do an open traverse, that is going to start and end at a completely different point, but the starting point and end point should have known positions, known location. Any questions? Some errors and mistakes with traversing. The instrument must be set up directly over the point and level. Use the leg clamps of the tripod to get the instrument close and over the point. Try to fine tune, level, yeah. So some big problems that could potentially happen here, being over your point or not over your point. A big source of error right there is parallax. I think I've said that like a couple hundred times over the last few times we set up instruments, where you need to make sure your targeting crosshair or targeting bubble is in the same focal plane as the object you're looking at on the ground. When they are not on the same focal plane, if you kind of move slightly, it looks like that targeting bubble bounces around your actual point. Parallax bad. I think in the future I'm going to add some of this stuff here, like using the leg clamps, and break this down a little bit more and actually have some more instruction on setting up total stations. Also, some other ones there, just like I said before, making sure you're not over the point. Setting the tip of a plumb bob. Who uses those? Or setting the rod or whatever you may have not on the actual point. It's important to keep track of all your bearings, your forward bearings, back bearings. Make sure all angles are turned from the back sight to the foresight, usually clockwise. Recognize how deflection angles are measured so they can be drawn correctly. Check adding of degrees, minutes, and seconds. Always, always, always include leading and trailing zeros in the angles. So if you have an angle or a bearing or an azimuth of 54 degrees, 4 minutes, 12 seconds, something like that, for the 4 minutes, it's always good practice to keep that leading zero in there. So it would be written as 0 4 minutes. Good practice. So again, kind of keeping in mind about bearings. Northeast bearings are turned from the north to the east. Southeast bearings from the east to the or from the south to the east. Southwest bearings from the south to the west. Northwest bearings are turned from the north to the west. Azimuths are all from the north, measured clockwise. And maybe some of you may have seen in CAD or Civil 3D entered bearings by quadrant, 1, 2, 3, 4, 1 being northeast, so on and so forth on around. Yeah, then we just talk all that good stuff. Wow, look at that. I forgot I went through a little animation phase in there. So we also looked at, when we did that horizontal angles lab, we looked at our misclosure. I don't think we actually calculated the misclosure, the permissible misclosure, where the actual misclosure would be the formula that we use, that n minus 2 times 180 to find a theoretical sum, and subtract that from the actual sum of the interior angles that we actually measured. Yeah, good stuff. Thank you. Good night. Come on, guys. I know this is highly riveting stuff. Keeps you on the edge of your seat. Especially these should be world famous, exciting PowerPoints that, yes, I am working on to make a little bit more engaging and better. Talking about distances. Distances generally regarded as the most fundamental of all surveying observations. So again, if you think of like the horizontal angles, you can take indirect angle measurements by measuring triangles, measuring distances, and applying a little bit of trigonometry to calculate those angles. In plane surveying, the distance between 2 points means horizontal distance. Pretty much every distance that we measure or at least want to know the value of is going to be a horizontal distance. The only other one would be a vertical. We generally do not concern ourselves much with slope distances. Land surveying in the United States is measured in feet, and we divided the foot into decimal, tenths, and hundredths. And I think the easiest way that I can kind of make sense of that is thinking of like a dollar bill, or 1 foot is a dollar bill. Break that into tenths, you're looking at dimes, you're counting dimes. Break that into hundredths, that would be like a penny. If everybody understands a dollar and dimes and pennies, that's pretty much the way surveyors break down decimal feet. Some of the methods that we looked at and studied were pacing, chaining, taping, stadia, and total stations. Everybody remembers that fun distance lab, right? That was like the most fun ever, wasn't it? Best lab ever? Or was the horizontal angles best fun ever? Which one did you guys like better? Yeah, me too. Seriously though, give me a little bit of feedback. What did you guys think of that horizontal distance lab where we did the pacing, the chaining, the taping? I'm gonna remove the stadia and the total stations. What do you guys think of that general, like learning about measuring horizontal distances?
A little boring, but it was cool.
Yeah,
We didn't really use the total station.
yeah, we just kind of set that up and shot it real quick.
I probably let them work on that. Then like the taping.
Yeah, so I would like to get rid of the stadia and spend a little bit more time with the total stations. That is, I'm glad you brought that up because that is something I am considering for next, or how to implement that. Another thing I'd like to do, I kind of called an audible on that really quickly and changed that lab quickly because typically it was done outside. And if you remember at the beginning of the semester, we had like feet of snow outside. So I don't know. I guess I could have stood inside and just watched you through the classroom window while you guys performed this anyway. But out of the kindness of my heart, I didn't want you guys to suffer out in the cold. But the distance measurements, very crucial, and it's good to kind of learn and see some of the historical methods of like the chaining, how that was done, what that was using that Gunter's chain, and then taping when we introduced the steel tape, which was graduated a heck of a lot more precisely than the Gunter's chain. Real quick, how long is the Gunter's chain? 66 feet. You get a gold star for answering. Um, yeah, so I don't know. I think it was kind of fun pulling the chain and letting you guys see all that stuff. Just see how that was done kind of historically. I would like to get that lab back outside and introduce a little bit more hillside for you to really struggle with. So we talked about pacing. It's the least accurate of methods, but very valuable. Is great for recon, some quick checks, some general, really, I don't know if I'd really even say layout. Quick checks. Oh, how long is it, or what's the width of this? What's the length of that hallway? You can pace that out pretty quick. What's the width of this room? You can pace that out really quick. You can get a rough idea. Doing a boundary survey. Okay, I got to go from this corner where I'm standing to the next property corner 300 feet away. You can pace that distance and get yourself in the general ballpark of an area. So some errors involved with that. You got personal, natural, and environment. Natural environment or method. The personal could be inconsistent pace lengths, miscounting or losing track of your paces. And I did try to introduce a little bit of shenanigans in that by throwing out random numbers while you guys were walking and counting. I enjoyed that. I'm impressed that I don't think anybody did lose count. Not that I remember. Natural errors would be like the slope or the terrain. Pacing follows the ground, but we need horizontal distances. And method could be poor calibration against a known baseline to calibrate how long is your pace. Expecting better precisions than can actually be achieved. Smaller per pace errors accumulate over long distances. I thought this was really kind of fascinating too. Just share this. Had a remote student come in to do this pacing lab. And when he calculated his pace factor, how many steps per 100 feet, he had something out to the nearest hundredth of, he came up with something to the nearest hundredth. So when he walked that line to say, okay, how long is this? One time I think he used his pace factor to the nearest foot and came up with a number. When he used it to the nearest hundredth, his distance changed by close to 10 feet. Which kind of also was interesting to show right there that like that's a cumulative error that adds up with every step you take. So the old Gunter's chain, it was developed to standardize measuring, 66 feet long, made up of 100 links, each link being 67 hundredths of a foot themselves. It was brought over to the United States colonies and had been a standard of measurement for the land surveyor until the early 1900s, being replaced by the steel tape. Pretty cool, pretty fun. So some errors associated with chaining could be misreading the chain, miscounting the number of chains and or links. Instrument error could be calibration, wrong lengths from where, every distance off the same proportionate. Method errors could be not staying on a straight line or non-horizontal measurements on a slope. So it's important to have somebody in the back watching the person in the front as you move from one point to another, trying to keep that person on line. So you try to measure as straight of a line as you possibly can. So as the United States became more industrialized and developed, the need became apparent for more precise measurements. So the 100-foot steel tape came into practice. It was lighter than the chain, easier to read, has more precise graduations, so it has to the foot, tenth, and hundredth of a foot. So some personal errors could be carelessness and misreading graduations of the tape. The instrument errors could be poor calibration, wrong lengths from where. Method and procedure. So you have temperature, sag, tension is not taken into consideration or accounted for. The steel tape was designed from a temperature and sag corrections, and the chain usually wasn't. We didn't really dig into that one too terribly much, at least the temperature and sag corrections and things to that, because this is not something people do for very long distances anymore. But again, zigzagging and potentially taking vertical or slope measurements. Here's your differences. I don't need to read all that, do I? So we talked about Stadia. This is, I think, kind of nice to know. When we went to Washington, D.C., one of the events that they did was a 3-wire level where they had to read rod readings on the upper stadia, the center crosshair, and the lower stadia hair. And they were graded on how balanced they were with their backsights and foresights, meaning was your backsight distance and your foresight distance close to being equal. That's an ideal situation. That's about the only time if you're really going to ever shoot distances this way. This method can yield distances to the nearest foot. Stadia constants also usually constant is 100. So if you read your top stadia hair and your lower stadia hair, subtract the difference between those two, multiply that by 100, that will get you your distance to the nearest foot. Personal errors associated with this, parallax. Ooh. Reading incorrect measurements. Instrument error could be in need of calibration, not holding the rod plumb or not holding it vertical. The numbers on the rod could be worn down and illegible. Some conditions could be long sights reduce the clarity of the rod, atmospheric shimmer and refraction make reading more difficult. Aim for good habits, not perfection. I would also recommend that pretty much in anything you do in surveying. Aim for good practice, good habits. Now we have the robotic total stations, the EDMs. They measure lengths and horizontal lengths indirectly by shooting out electromagnetic energy, traveling from the instrument to a prism, coming back to the instrument again. Knowing the wavelengths, it does all the fancy math to give you that. Total stations are measuring slope distance. They are also measuring the vertical or the zenith angle and internally calculated to display horizontal distances. That is key to remember. Just saying that's important to remember. Stuff like that may or may not be on the final exam. Errors associated with total stations, the instrument and or the target may not be centered or level or over the points. Using incorrect prism constants, not taking into consideration atmospheric conditions. Heat waves, fog, dust, heavy moisture, strong vertical temperature gradients can bend or weaken the signal. Subtly biasing distances or making readings unstable. The correct setting of geodetic or plane surveying with the proper datums and state plane coordinate systems. Correct unit settings. Is that it? Oh my gosh, it's over already. Go away. Jump in this one real quick. Oh, this is where we start getting a little more fancy with our PowerPoints. Oh yeah, going through the old animations. So talking about some of these, talked about the total station characteristics, equipment components, setup, which I need to add more to, and angle measurement methods, error control, and angle observations. The old evolution of surveying instruments. They first started out with a compass, transit, then theodolite, and then moving to total stations. Total stations combine the standard theodolite and the EDM. The result of that is automated measurements and instant calculations. Again, it's important to see, learn, understand like the whole compass and the theodolite to understand like how closely surveyors could actually measure things. So when you get out there with your total station or your GPS and you're like, this thing's off by, you're measuring two monuments that might have been set in the 1800s. And you're like, man, this thing's off by like 5 feet. Well, that might actually be pretty good considering the terrain and the conditions they were surveying in at the time. So the total stations, they measure horizontal angles, vertical angles, slope distances. And from these measurements, that computes horizontal distances, it computes elevation differences as well as coordinates. It will only compute coordinates if it knows where it is, has a coordinate value for the position it's occupying, and a reference baseline to establish direction. . . . So there's some key systems: the telescope, the EDM portion, the angle measurement system. They all work together to produce survey measurements and coordinate calculations. I think I might hijack this off of Trimble's, just talking about various components of the total station. So 3 critical geometric axes would be the vertical axis, the horizontal axis, the line of sight. Movements that are important are the rotation about the vertical axis for horizontal angles and the rotation about the horizontal axis for the vertical angles. Proper alignment of these axes are critical for accuracy. Yeah, good fun stuff here. But they perform many computations automatically. The total station that the data collector that we use. So telescope and sighting. I just want to kind of point out again here, one of the big things is proper focusing to eliminate parallax. Again, you want to get your crosshairs into focus to your eye. Then you want to bring the whole big picture into focus. So the crosshair and your target are in the same focal plane to eliminate parallax. I just only repeat that. That may or may not have something to do with the final exam, but that is just a good bit of information to know in general. This is just, I think, talking a little bit about aiming with the auto lock versus manually sighting a target. So yeah, those robotic total stations, they will manual or automatically lock and follow your prism. But where would the fun be in that? That's gotta get you guys a little experience with manually turning and sighting prisms and targets. And there's the parallax error that I like to harp on. So the EDMs measure angles electronically. Digital reading of circles, resolution typically 1 to 5 seconds. And these measurements appear instantly on the instrument display, or in our case, on the data collector we used in Survey Basic. I believe all of the S5 total stations that we have are all considered 3-second instruments, referencing their angle accuracy. I need to go through and redo all this here. So I kind of was breaking this down into 3 separate sections. This is also very important to know. Your initial set the tripod up, get the instrument attached. Rough center over the point, rough leveling. Break that down into one section. Your roughs, we're starting out with a wide base here. Rough setup, rough level, rough over the point. After we do that, then we start moving into more of the fine tuning, where we readjust the center over the point and we do our fine leveling. From there, we go into like the refine moment if needed, double check and center over the point if needed, and double check, make sure the level is still good. An accurate setup is crucial for precise measurements. It's also essential. It's crucial and essential. Leveling ensures the vertical axis is truly vertical. So here's the old left thumb rule. Turn both screws in, turn both screws out at the same time on your one axis. The direction of your left thumb going either in or out will determine which way the level bubble goes. Left thumb rule. Learn it, live it, love it. Yeah, so here's some stuff with these. The S5 that we use here at school has the servo motors, automatic prism tracking, and remote control operations. Benefit being one person serving. I don't know if that's quite a benefit. Increased productivity, improved safety. I'm not too sure about that one either with one person. Can be common in construction layout, which I'm not a big fan of. Only because I did one person construction layout for many years. Not a fan. Relationship between angles and distances. Small angular errors can create large positional errors. High precision angle measurement is critical for accurate surveys. This is kind of a good thing to know. This may and or may not, probably not be on the final exam, but it's just some good information to know for you future surveyors. When observing angles, you want to set up level the instrument, sight your back sight point, set 0. That is essentially establishing your reference baseline. From there, you turn to your foresight and record the angles.
When do you flop the scope?
Yeah. Oh, when do you? That's typically for situations where you're either setting control or maybe locating some monumentation. You would want to flop your scope. If you're doing some basic topographic, where you're just kind of locating some existing features, ground shots, things of that nature, one direct measurement's sufficient. Construction layout, usually you just use the direct. But when you're trying to get more precise, more accurate angle readings or being able to check yourself, setting controls, locating monumentation, you would want to do that direct and indirect flopper scope. Great question. What else you got for me? I'm dying to answer questions. What you got? Anything. Angles are often measured in the direct or reverse position. I typically would say direct or indirect myself. This is the reason for doing that is to reduce systematic errors caused by instrument misalignment. The final angle would be the average of both observations, your direct and indirect measurements. Remember how we kind of talked about that there? If you, to example and to over exaggerate, if you were looking this way through your scope and then you flop, you're going to be over the same amount off. So the average of those two should snap you right into the middle.
So that's what I was asking.
So yeah, if you're doing a boundary survey, locating some property corners, be a good thing to do. Running a traverse to set control, you'd want to flop the scope. In this day and age with GPS, we can't flop the scope. However, what we do is take multiple shots on a point to be able to do a statistical analysis, say, hey, we can repeatedly hit this position within a certain error size, which we will get into in the geospatial control class a little bit more in depth. Does that help answer? Does that make sense? Clarify? Repetition, measure angles repeatedly, accumulate readings, divide by the number of observations. Benefits of this: reduce random errors and improves precision. is, I like to say, redundancy builds confidence. And that's not just for the total station. That's even if you're using a GPS. You want to take multiple observations of the same point and get that redundancy. From the GPS standpoint, get into that more too in the geodetic class, surveying class. Oh my gosh, that's it already? This is some semi-important stuff to know that may and or may not be on the final exam, talking about the land tenure system, which here in the United States is a way land title and property rights are recorded, held, and transferred, primarily through written instruments and public records at different levels of government. So with the survey plat, we looked at a written document that explained and described a certain piece of land. That is part of the tenured system. So the United States uses two-tier land tenure system with federal records governing federal lands and state and local records for other lands. That local, I'd say probably state and county would probably be better. You're going to mostly go to the counties that you're working in to research your various instruments, written instruments. Land titles are transferred by written documents called deeds. There are various types of deeds depending on what you need them to do, which contain a description of the property, and these written recorded deeds are central to how tenure is maintained and proved. Title versus ownership. There is a difference, and per the surveying book that everybody should have at some point or another, not necessarily now for this class, but one to have and keep in your personal library is Brown's Boundary Control and Legal Principles. I could be wrong, but I think for the surveyors, when you take a boundary control class, is probably a required text. So title is the means or authority by which one justifies legal possession to the property. It is not ownership, but evidence of ownership. Title to real property may be transferred by voluntary means, involuntary means, or inheritance. The common method of voluntary transferring title to real estate are by grant deed, quitclaim deed, warranty deed, easement deed, and will. Ownership is described as the legal right to possess and use the property. It is the underlying bundle of rights in the real estate. Different forms of ownership are outlined: sole ownership, joint tenancy, tenancy in common, community property, condominium, cooperative. All are variations on who holds legal rights and how they are shared. There are leases, there are licenses. I think most people have probably heard of leases before and is related to property. Somebody owns a piece of ground and leases the rights to use that property. A license is personal permission to do something on another's property, but does not create an interest in the land. So I guess the easiest way I can think of to maybe describe a license would be anybody who might be a season ticket holder to the Bengals or something like that. You have to buy a seat license in order to be able to get your seats. That seat license is basically this. It's giving you permission to go into the stadium and use the stadium. However, it does not give you interest on the property that the stadium's on. Now it all makes perfectly sense and justifiable to spend that money on the Bengals, right? Or a football team of your choice. Not that anybody would want to for the Browns or anything. I'm kidding. I'm kidding. Easement is a right by grant or agreement which allows a person or persons to use the land of another for a specific person or purpose. It always implies an interest in the land on which it is imposed. Black's Law Dictionary lists and defines 18 types of easements. So the exact purpose of an easement should be clearly stated. A lot of times you'll come across things like a utility easement. Its sole purpose is for a utility to cross someone else's property. Ingress egress easement could be for a person or persons to access through the property to go to maybe another property or something like that. Many types of easements. We won't get into all that. Legal descriptions. Meets and bounds describes the property by distance and directions from a point of commencement to a point of beginning, referencing monuments, adjoiners, and other physical or recorded calls. The meets of a meets and bounds description is the directions and distance, the bearings and distances going around the property. The bounds of a meets and bounds would be referring to the adjoiners in the sense of bounded by so and so on the south, so and so on the east, so and so on the north. Calling out the adjoiners would be the bounds portion of a meets and bounds. A description of land by meets and bounds in a deed should always contain at least the following information. This is important. It may and or may not be on the final. These 6 things that are needed on a meets and bounds description. Your point of commencement, point of beginning, definite corners, lengths and directions of property sides, names of adjoining property owners or abutting highways, and area of the parcel. Does anybody got any questions on that? Do I need to go through all those definitions? Again, it's kind of important. 6 things that a legal description by meets and bounds should always contain. Other types of legal descriptions, we have a block and lot system. This is what a legal or a deed you would find for somebody who owns a lot in a recorded subdivision. That is basically going to say that the legal description is not going to be much more than being lot number whatever of whatever subdivision recorded in plat book page whatever. In that case, you come across a legal description or a deed that has a lot and block description, you would need to pull the subdivision plat, and that would give you the meets portion of how the shape and size of the property. So I always kind of wondered myself as a surveyor when I do courthouse research to find deeds, to find survey plats and subdivision plats. I always wondered, like, why are survey plats recorded with the engineer's office and subdivision plats are with the recorder's office? I'm talking about Ohio specifically here in this case. And that always kind of confused me, like, why aren't subdivision plats with like survey plats in the engineer's office? To me, it just never made sense until I learned. of the lot and block system, you get deeds from the recorder's office. Therefore, if it is a lot and block, you need to have the subdivision plat. So that is why they're right there in the same office as your deeds, the subdivision plats. Did I say that clearly? Does that make sense? In Indiana and Kentucky, Ohio, you go to like the auditor's office, the tax map, which is a portion of the engineer's office. We have the county recorder, which has deeds and subdivisions. Indiana, Kentucky, you have assessors or the PVA. Uh, things might not be in the recorder's office, but the county clerk's office. It varies by state how they do that, but it's still kind of a similar setup as far as where things are stored. Just the offices may be named differently. So there's a legal description from an actual deed. As I said, situated in section town range of the Miami Purchase and the township. Being Lot 2 of Block B, Section 3 of the Brentwood subdivision, as recorded in Plat Book 72, page 87 and 88 of the Hamilton County records. That's a legitimate one I really pulled from Hamilton County. Other types of legal descriptions are fairly rare. I know some people really are kind of liking the idea of using coordinates to describe property corners. If this is a system being used, you need to have quite a bit of metadata associated with that. And what I mean by metadata specifically is how are those coordinates derived? So if you are using your GPS and you're just going around popping off all your coordinates on all your corners, what reference datum are you using? That is important to know. Or if you just ran traverse and you assumed coordinates, that's still important to know for the person coming behind you who may be surveying in the future. Reference datum, state plane coordinates, again, that's kind of, we get really into depth in that with the geodetic surveying class. As much as I've been saying that, I feel like I'm starting to kind of become a commercial for that class. Hey, this summer, sign up for it. You need to have this class. It's fun, it's exciting. Public lands, the public land surveying system, also usually referenced as the PLSS. Areas surveyed, administered, and disposed of under the federal public land laws since 1785, covering about 72% of the United States and 30 public land survey states. So in the New England colonies, New England states, the original colonies, Kentucky, are known as like meets and bounds states. They are described as, just by bearings and distance, things like that. The public land system, the government decided early on, like, hey, we need an easier way to sell and for settlement. So they came up with this essentially like a checkerboard system. That's where the public land system comes from. Ohio was one of the first states, and the government kind of played around in Ohio trying to figure out, hey, what's a good method of subdividing this land? For the most part, it's all the same as far as 36 sections make a township, make a range. Your range lines are running depending on where you are. There are some differences there. Some range lines run east-west, some range lines run north-south. Township lines, same thing, opposite. And then once you get down into that, into the individual sections, how they started numbering those changes depending on the Land Act from somewhere in the 17 to 1800s. That you get into more of on the at least all the different acts, land acts of how they subdivided the land, how they determined how they were going to label it. You get more into that in the history, surveying history class. I do not teach that, but I still want to push it anyway. It's a pretty fun class to learn about. And if you do want to become a surveyor in Ohio, knowing these land acts are very important for your Ohio specific exam. Yeah. So there's a lot to these early manuals. Um, the BLM is the Bureau of Land Management. It's the administrator today of remaining federal public lands. Fun little story. When I was in DC, I was talking to a guy in Ferris State, a student, and he was talking about working a seasonal job with the BLM. In the summers, he goes up to Alaska and surveys. Sounds pretty cool. I'm not sure my family would like for me to take off for like a month or three to a couple months to go survey in Alaska, but maybe while you're young, before you settle down, create a family or whatever, might be kind of fun experience. I know it's not the easiest to see. This the slide deck is also on Brightspace still. This shows the areas where there are meets and bounds as well as the public land surveying system. I could just sit and look at maps all day long too. I think they're pretty fascinating. So here's kind of the framework and geometry. System starts from initial points being principal meridians, which run north and south, and baselines, which run east and west. Then builds out in standard parallels, uh, correction lines, guide meridians, and 24-mile quadrangles. Quadrangles are subdivided into 6-mile townships. Townships into 1-mile sections. Ideally, there should be 36 sections per township. Read more into it. It's pretty fascinating. And again, too, before flight was invented by whoever you want to believe that is, whether it's Orville and Wilbur or somebody else, I don't know. But when they started running from the south, running north, and then their meridian lines, and when they'd start cutting across baselines, they were expecting a distance. And as they went further north, that distance kept getting shorter, kind of proving that they were converging, which also kind of helps prove that the Earth is not flat. So you don't need to be up in space or high up to see the curvature of the Earth. You can measure it on the ground. I'm not going to get into a whole heck of a lot of detail with this right now. Unless you want me to read all this. I'm amazed all of you are still with me and I still see as many eyeballs as I do. There's a strong emphasis on corner marking, original monuments versus modern iron pipes, brass cap stuff, and the use of bearing trees and witness corners. I think this is part of part of the chapter 22, where this is taken from. Talks about meander corners, meander lines, things to that nature. Section 2219 distinguishes obliterated versus lost corners, describes single and double proportion measurement methods for restoring them. For those who are going to be surveyors, I would strongly recommend, especially if you're working in the PLSS, that sort of stuff is very important. The difference between lost and obliterated corners. An obliterated corner is one where the original monument is gone, but its position can be recovered with convincing evidence. A lost corner is one where the position cannot be determined beyond reasonable doubt and must be recreated by proportionate measurement from other corners. So obliterated, the corner's gone, but there's enough evidence, maybe ties or witness things that you can pull back in to establish that corner. Restoring evidence like old witness trees, fences, walls, occupation, testimony. And lost corners, nothing is there. So there's not even any evidence that you can restore that corner from. Any questions on lost and obliterated corners? So I think of it as like my glasses. I step on my glasses. I know where they are. They're right there. They're just in pieces. They're obliterated. When I set them down, walk away, and can't remember where I put them, and I have no way of finding them again, it's lost. By today's modern standards, these early PLSS surveys were low order. The text lists historical causes of poor quality and today's challenge in retracement, equipment limitations, convergence, water course changes, and non-permanent marks. So a lot of those guys too, when those surveyors were coming through establishing all these originally in the early 1800s, they're setting a wood stake. What are the odds of finding a wood stake that was set in 1802 today? Probably not going to. So check up on chapter 22. There may and or may not will be some information in there that will be maybe on the final exam. I really got to make these PowerPoints better, don't I? Did I go over it? Holy cow, we're almost out of time already. Where did my paper go? Well, here's what I'd recommend. Chapter 17 is going to be one of the things on there. Read, study. The exam, unless I did not say this before, is 3 hours. It is also open book, open note, so you can have all that stuff, class notes, anything you may have taken. Feel free to use during this 3 hours. You have until Friday night, midnight Friday night, to complete it. Does anybody got any questions on any of that stuff?